In the following series of video lectures, we are going to be learning how to use Gauss-Jordan reductions to solve a system of linear equations. A system of linear equations is just two or more equations with two or more variables in them. A standard system of equations would look something like this. We have three equations here, and we want to look for a solution that will solve all three of these equations at the same time. That is, we're looking for a value for x, a value for y, and a value for z. The first thing, if we're using Gauss-Jordan reduction as a method to solve these equations, is to write our system of equations as a matrix. Notice that the initial equations all are of the form where you have something with x, and then something with y, and then something with z. Then you have an equal sign, and then you have a number that's after that. When we set up our matrix, it's really important that our equations are in this form before we begin. When you look down below, here I've set up a matrix. There's 3 rows, 1 row for each of the equations that we have. Now, notice that there's an x column, and the x column is where we have all of the coefficients for x. Remember, a coefficient is a number that appears in front of that variable. Then we have a column for the y, those are the numbers that appear with the y, a column for the z, and then a column for the plain numbers that appear on the other side of the equal sign. Here's our first equation, 2x plus 3y plus z equals 4. Notice the numbers in each column correspond with the numbers in front of those variables. So 2x plus 3y plus z equals 4 has a 2 in the x column, 3 in the y, 1 in the z, and then a 4 in the number column. We want to go through and do this for each of the different equations. The second equation here, again, where it's just x, there's a 1 that's assumed to be in front of it. That minus 5, the negative stays with the 5 as part of the y coefficient. The z has the 2, and the number column has the 13. In the final row, we have the 4 in front of the x, again, the implied 1 that's in front of the y, a negative 3 in front of the z, and then the negative 2 that's after the equal sign on the other side of the equation. Now, this is our starting matrix. What is our goal? Our goal is to get to what is called reduced row echelon form. There are a couple of requirements for a matrix to be in reduced row echelon form. The first requirement is that the first non-zero number in a row has to be a 1. So we want this top number here to be a 1. Once you have this value to be a 1, this is called a leading 1. Any other number in that same column, so any other number in the x column, has to be a 0. So this is part of our requirement for reduced row echelon form. When we go on to the next row, again, we need the first non-zero number in that row to be a 1. We already needed a 0 in this row, so we need a 1 in the y column here in row 2 to get this nice form. We need these numbers on the bottom row to be to the right, the ones to be to the right of the ones that were in the first row. Once you have a leading 1, every other number that's in that same column, so all the other numbers in the y column have to be 0. When we get to the third row, we already have these values defined. We need the next value, so the first non-zero number in the third row to be a 1. There it is. And then everything else in that column with the leading 1 has to be a 0. And there those are. Now, we have defined now the first non-zero number in each row is a 1. Whenever we have a leading 1, every other number in that column is a 0. And we have each leading 1 is to the right of the leading ones that come prior to it. So that means that there are no requirements left on our number column, and these numbers will be whatever they come out to be. Now, why is this form so nice? Well, notice that if we translate everything in each row back into an equation form, that what we end up with is some really nice equations, such as the first row tells us x equals a number, the second row tells us y equals a number, and the third row tells us z equals a number. That's fantastic, and that's what we're trying to solve for. So if we can get our matrix into this form, we will know the answer to the system, which is our goal. What can we do to get a matrix into that form? They're called legal row operations, and they're things that we can do to the rows of a matrix to convert it into reduced row echelon form, there are three possible legal things that you can do to create an equivalent matrix. The first is just to switch any two rows in the matrix. So you can switch row 1 and row 2. Again, you're treating the row as a whole. Another legal operation that you can do is to multiply or divide an entire row by a non-zero number. If you want to multiply the whole first row by 5, that's great. If you want to divide the whole second row by 3, you can do that too. The third legal row operation, and this sounds kind of long, it's to add a non-zero multiple of one row to a non-zero multiple of another row, and then replace either row with the result. It sounds complex. As we do some, you'll see how really cool this is, and this is going to allow us to really move forward and simplify our matrix to what we want it to be as we go through. These three things are the only legal things that you can do. What these do is create a new matrix that's equivalent to the old matrix and has the same solution. So what steps do you want to do? Here we have this matrix. Here's the matrix that we want to come up with. We have only three things that are legal that we can do one at a time to try to get into this form. How do you know what to do first? It's pretty open-ended. Well, let's tune into the next set of videos to find out. What I will be showing you is kind of a foolproof method. There's a lot of different ways to solve each problem, but what I'm going to show you is a step-by-step method that you can always do. If you don't know what to do next, there will be a series of questions you can ask yourself every time so that you always know something productive that you can do to get yourself into RREF form. Tune into the next video and we'll go through a couple of examples. Thanks.